continue with the next session. So this on emissive systems, and we have an invited lecture from Pleasure to be started.
Thank you. Thanks. I want to tell you a story about emissive devices relating to liquid crystals in particular. And one of the reasons in the last few years, is this too loud? Okay. Is the voice okay?
It's great. Yeah.
Okay. One of the reasons is that many of the constructional methods used for displays you can use in lasers. And if you look at a liquid crystal laser, you can almost imagine it as a pixel. Okay. What I do have to do for this talk is thank particularly Phil, Steve Morris, Tim Robinson, who've done a lot of the measurements, but I want to take you back a few years, 3 or 4 is a few years in this game, and then bring you up to where we're at today. And of course, Ivan Noel for the invitation and the chance to come and talk to you. I'll mention where the work has been funded by our NPSRC, Cosmos that Phil mentioned yesterday, some of the materials from Merck, and some from ALPS. ALPS is a Japanese company for whom we're trying to use this work to make a microscopic holographic laser projection element. But when you come to the end of the talk, what I can tell you is we have actually shipped one to Japan at the moment. So I'll give you the background, talk about what it is you need to worry about in liquid crystals, why we went on to bimesogenic, what experimental conditions affect your lasing, and how you can make that lasing much more efficient. And then a little bit at the end on the lasing blue phases. And of course blue phases have become very important in the last couple of years. One, in principle you can make 3D lasers, but 2, you can make very fast, high-speed frame rate displays. Right, perhaps talk about that at the end. So you should by now be familiar with the idea of pneumatics, chiral pneumatics and twisted structures. Then what textures look like for the two systems, the Grandjean texture, and then chiral symmetrics, the blue phases, in their fairly non-aligned states. Again, I'll come back to those. If you're interested in the classical laser, you normally talk about some kind of amplifying medium, input pump light, and then you look for a threshold and an amplified gain. So what we want to do is lower the threshold and try and increase the slope efficiency. Okay, and that's what we want to look at, improving pump efficiencies. Just a little bit of background physics, it's not crucial for following the talk. In these kind of laser systems, they're a little bit like distributed feedback systems, but they're not quite. The group velocity goes to 0 at the band edge of the chiral pneumatic or Collis carrier. The little 4-head thermometer devices you probably have described on Tuesday. What that means is the density of states at the band edge goes to infinity. So the photons are very long-lived. Okay, and this has all been explained and described in the literature. These references occur with the abstract you get on the website. What I'll firstly do is talk about chiral pneumatic liquid crystals, helical structures, how you put a laser together, and then what matters. So you take a chiral pneumatic, a chiral structure, you shine that light along wavelengths in, you get reflected light and you get transmitted light. And you get the so-called photonic band gap. And as Phil said yesterday, you get a long wavelength edge and a short wavelength edge. And that's just depicting the chiral structure. Normally you talk about light at one-handedness, but you can in fact, construct lasers to give you both handednesses in your system. So what you normally do is say, right, here's the selective reflection, here are the two band edges, which are the short wavelength and the long wavelength where lasing can occur. So the ingredients, first of all you need a gain medium, so you have a fluorescent dye. You put that into your chiral pneumatic, and so you end up with the reflection band and the absorption of the dye, with the emission coming out, hopefully, peaked at the band edge. Okay, and if you constructed your system right, then you will get very strong lasing at the band edge. Very narrow lasing, as I'll show you. A schematic of that is put green light into your system. We normally use a pump of 532, but we have used other systems that I'll show you. You get the reflection mechanisms within the cholesteric, and normally light of a long wavelength coming out. So if you looked at a typical experiment, we have 4 or 5 of them running. That little orange element in there is the liquid crystal laser. It's a cell about centimetre by centimetre, with an active area of probably 5 millimetres by 5 millimetres. But when you think that the diameter of a typical lasing spot in a liquid crystal laser is perhaps 20, 30, 40 microns, that gives you many thousands of potential lasing channels. Well, again, we'll come back to that. So, what the experiment is, you pump the system with green light, 532, you put a filter into your system, and you'll see red light coming through, if you've got it working right. And that's just another picture of the same thing. So, this is actually lasing in band edge from one of our systems. And you can see that there's your reflection band, and there's the laser line coming out right at the first minimum of the carbon reflection. You get almost perfect Gaussian laser lines. Okay, if you align your system again, as I'll show you, you tend to get something approaching a Gaussian angle profile. Is that your projector going down here? Yeah? He gets tired. Sometimes when we travel all around the world. It's very hard to describe an area that is coming up on the tip on the screen. But it looks a bit like that. Gives me a chance of a gin and tonic anyway. You need a liquid crystal laser projector.
Go back to that. I'll put it on there. Did you guys push really hard on the button?
It's on the screen right now. Yeah, if you have a liquid crystal laser projector, you won't have this problem. Oh, you won't have this. Okay, what I was going to describe there is coming up out of the background is the far field area design pattern. And the key thing is, with these kind of systems, you have something like a 5mm, perhaps 6mm coherence length. And the reason why that's important in our short-range projection. What is important with these lasers just about here then, we've got our laser system pulsing, and as you move the cavity around, the light is always orthogonal, the cell sitting in here, the light is always orthogonal to the plane of the liquid crystal device. So no matter what angle you pump the system with, your input light, your light always comes out on the helix axis. And a lovely demonstration of that is just there, taking the same liquid crystal cell, pumping the system as we do classically, so the chromatic axis is along the direction of the beam, and you get your red light, you just see it in your green light. Or you can end-fire this, or you can cycle-fire the system and get lasing out. In this case, the axis is towards you, and you get orthogonal lasing. So you can actually play with that tells you can play with the illumination system to make an efficient laser. You do have to align the cholesteric if you want to get all the carbomatic, if you want to get a good narrow ion width. So that's a typical well-aligned carbomatic cholesteric sometimes called. And you can get monodomain output with very narrow ion widths. Okay? If you have a polydomain sample, as Phil said yesterday, you will get a multiplicity of lines. Now for some applications you might actually want that. For this one we don't. What I wanted to do was just say any of you can make a liquid crystal laser. Okay? Any of you. Because you can make them with simple cyanobyte fields, you can make them with some of our bimesogenic systems. And I brought these structures up to show you that they perform differently depending on the chemical structure. And there it tells you that for the same kind of excitation systems, the same helices, if you look at the classical E49 and E7 mixtures, E7 is down here somewhere. E49 is a slightly better material, that's in there. And BO37 is quite good. And you can get those materials from Merck, and then you can use them to play around with what's important for a laser system. Okay? What you will start to see is, if you look at the numbers on the left and on the bottom there, you're getting something like 10% slope efficiencies. Okay, so 10% of the light you get out. And that's with the bimesogenic structures. You also lower the thresholds. In a liquid crystal, you have to worry about order parameter. And I just put this data in to show you that under the same illumination conditions, if you increase the order parameter, you increase the output of the light. So that's one parameter that's important. With some of the bimesogens, you do get some temperature dependency, but it's very easy to get 10% slope efficiencies. You can make materials where you have no temperature dependency. That depends on the kind of composition that you put together. You also want to have fairly narrow beam diameters. But if you just look at that scatter of data, if you have a large beam diameter, you get much lower output than if you have a more tightly focused material. In fact, ideally you want to go down to about 10 microns, but when you go down to about 10 microns, you've got a lot of photons per unit area. But if you do go to lower diameter beams, then you lower the excitation threshold and you increase the slope efficiency. So you do want reasonably tightly focused beams. But if you do that, you restrict how many pulses you can give to your system per second, because you start to bleach the dye or you start to get local heating. But in fact, you can get around that to a large extent by using reactive mesogens to cross-linking the structure. And we now easily get up to 60 Hz rep rate with some of the later lasers. You have to worry about sample thickness. So there are optima in the threshold energy and the slope efficiency, depending on how long you make your cell. The longer you make the cell, the more direct fluctuations you get, you start losing efficiency. Okay, so there are optima in around this 10 to 20 micron, thereabouts, part thickness. There or thereabouts. Experimental conditions matter. You can get E7, you can get E49. They all show these same sorts of minima in the threshold and maxima in the slope efficiencies for similar conditions. But there, the birefringencies are different. So the birefringence of the host is important. And that tells you that straight away. Okay. If you excite the system too much, then you start to see a roll-off in the output emission. Okay, it happens that E49 is the better material to play with than E7. E7 has lots of ester compounds in it, and horrible things you don't want to know about, but everybody still uses it. But it's not a very stable material. It matters what dye you use. Okay, you can use DCM, you can use the pyromethanes, and if you change the dye, and you change the dye concentrations, you see different efficiencies, different excitation threshold. So you want lower concentrations, and there are good reasons for that because of further bleaching, and you get higher slope efficiencies. But now we're talking about 23% slope efficiency, so that's the output energy over the input energy. And that's pretty high, would be even high for a solid state laser. So you go back and you say, okay, we know that our bimesogenic is pretty good. But what about E49? If we actually use the right dye with the absorption and emission bands in the right positions, we can get up to 29-30% slope efficiency. And pyromethanes are very good dyes. You can see the output there over the chemicals. Okay, you want to tune the system. One of the first things we did, we used flexoelectric tuning, where you align your helix in the Grandjean texture, so your laser beam will go up through the system, and then you apply a transverse field, and your layers tilt. or the helices deform, whichever. And these systems are actually used in display devices, but they actually work as a switching mechanism in the laser systems. So what you're doing is taking your laser beam up through the material. If you look at your chiromatic polystyrenic texture, helix, you get a distortion or rotation of the optic axis. Okay, that's very important for displays, and it's also very important for lasers. Because you can show that you can tune the wavelength to a certain degree as you apply a low field across your system, and the peaks move around in wavelength space. Now these aren't so good as the narrow line width that I showed you earlier, simply because the textures in that particular device were not well aligned. They were not monochrome Rorschach. But you can also put a slight wedge onto your cell, if you want to, and then as you change the pitch and you stress the system while you do a wedge, then you can actually again tune it by position, the wavelength output. Not massive tuning, but for many applications quite useful in telecoms, for example. You can thermally tune the system. You can make a chiromatic that is temperature dependent or temperature independent. If you have a temperature dependent system, you can tune the output laser wavelength by about 25-30 nanometers, just as a function of temperature. Okay, you can also use command surfaces, and this is some of the work that we published recently, where if you make a surface that you can switch the director, you can use that to tune the helix pitch in your system. And you can see what is quite nice in these low wavelength edge systems, is you can get wavelength changes from, let's say, 625 up to 725 nanometers, 100 nanometers tuning. Okay, they're all thereabouts. And if you're a laser physicist, what is important is the finesse. The band shape doesn't change as you switch the system. Okay, so you're maintaining your band shape. So you can actually use that as a very useful tuning mechanism. Blue phases. Without going into all of the structure of blue phases, what I'm interested in are the double twist cylinders formed to give you disclination lines that give you a cubic structure. And in a blue phase, the cubic defect structure gives you a selective reflection of light. That's all you really need to worry about. So near the disclination line in there, the director has an S minus a half disclination, just in there. But typically your structures are cubic, face center cubic, body center cubic, etc. And Peter Palfrey showed 6 years ago now, some very interesting lasing in a very carefully constructed device, showing you could get laser output in 3 directions simultaneously, right at the corner of the cell, providing you align your cubic lattice or face center cubic lattice correctly. Okay, and those are indeed the 3 lines that you saw. So you have a threshold, and then you have lasing output. So you can make lasers that are 3-dimensional. We wanted to do that with our blue phase systems. We published a few years ago, 3 years ago this summer in fact, a paper on blue phases that have very, very wide temperature ranges. I think that's the first time that had ever been seen. Had a lot of fun trying to follow the major process to get that published, by the way. Because one wrote reads it, it's absolutely fantastic, but he didn't believe it. And the other one said, yes, it's true, you should publish it. And it took a year to get them through the system, so not 3 weeks or 4 weeks. But it was fun arguing. So you make these mixtures up, and then what you see if you have an unaligned classical blue phase material, if you're up in the isotropic phase, coming down in temperature 57.4, 57.3, 57.29, you start to form blue phase 1, and then you flip 57.24 into 2, and then into blue phase 1. This is a non-aligned sample, so it's a polydomain sample. But what's important in this figure is if you come down to 25 degrees, the textures are identical. If you come back up and down, they stay stable. So you've got 30, 40, well, I haven't finished, probably 32 degrees in that diagram, white, blue phase. And we did lasing in that system, and again you saw a threshold and gain within the material. Okay, so background fluorescence and then the line coming out as you pump the system. And that was from a little, in this case, a little blue phase platelet. It's a devil to get a lot of lasing in a blue phase, because you've got to align the to work very, very carefully. So, can you do that? Yeah, yes, indeed you can, otherwise I wouldn't be telling you. First of all, you take one of these materials, and if you change the pitch in the system, you can have a red, green, or a blue reflecting film. You just change the pitch. So compared with the cholesteric, that would be the reflection band, the carbonizing. Okay, and you can choose whatever you like for the pitch of your system and therefore the wavelength of your system, just by changing the amount of chiral additive. And we use 1/2 chiral additives. For the work that we put into the Nature paper, this was the switching property, is as you apply the field across your system, you actually change from a red reflection to a green reflection. Take the field off and you go back to red reflection. I should stress there are no polarizers in this system, there are no color filters. There are no alignment layers. It's a simple, switchable color reflector and therefore color laser system. And yes, you do, and you can align the materials. These are millimeter areas that we align to show you the red, green, and blue reflection properties. Those are the spectra, and those are the switching properties of the materials. If you change the flexoelectric coefficients of your materials, that's the polarization you generate on information, then in fact you can lower the switching threshold down. But you get very nice, reproducible, reversible, and quite often sub-millisecond switching of the lattice through that restriction. Okay, so you can make large area monoplanes, you can change the chemical structure, and you can improve the blue phases. Now I want to go on to something I touched upon where I said, if you want to increase the reputation rate in your laser, you've got to think about saturation of the dyes. What Phil described yesterday was the lens lit array work that we've been doing, where we illuminate, you've got this, let's say 5mm by 5mm cell, and you can illuminate many hundreds of lasers simultaneously. So you get the laser outputs and lots of little red spots. So green in, that's the active sample, and these are the spots as you described yesterday coming out. Combine those spots with the far field and you again get these area type discs. Now if you want to make CW operation, you think how are you going to do that without saturating the dye? And what you would normally do is actually scan these sequentially, and therefore fire your laser sequentially. Okay, you could use an acoustic deflector for example. And that gives you very close to CW output. Now these are just descriptions of the spots. What I wanted to do was show you that there are dyes around already where you can actually make blue lasers, and Phil showed some pictures yesterday of green lasers, or indeed red lasers. So you can make quasi-CW RGB lasers. We don't want to, everything we've described thus far has been pumping the system with a frequency WR 5 nanosecond, thereabouts, pulse width. But this is the first work that we've done, and Phil's been doing with Steve and Tim, to actually say, wait a minute, we want to get away from bulky gravity lasers, or even small ESS systems. And what we've been doing and working on is actually LED pumped liquid crystal lasers. So green LED emission, and there is the first evidence we have of laser spikes coming out of the system. Okay, same with the blue pump, and again, laser spikes. Paradoxically, the long wavelength and perhaps the short wavelength edge. So I think these are the first LED pumped liquid crystal lasers I've seen. Certainly the polar dyes would fall amazing. And you've got evidence of the nodes sitting there in the edge structure. And there's pretty pictures to show you that you can get green and red light out of your system. So, I think that what you can do with liquid crystals is, first of all, it's not a complex fabrication. You don't have to crystal grow. You can use the construction techniques you already have available for you in displays, and the structure self-assemble. You can have, there are many different chiral phases. We've looked at chiral magnetics, chiral spectrics, blue phases, and even random lasers in spectric A. They're microscopic in size, so the optical half, as I said, is about 20 microns. Beam diameter is perhaps 10, 20 microns. So you're talking about a cavity, the width and diameter of a human hair, to put it into context. Okay? You can control the properties, and you can improve the efficiencies. And indeed, you can actually make plastic lasers if you want to, if you wish to, flexible lasers. Because you can make flexible chiromatic holosteric films. Ergo, you can make holosteric flexible lasers. Then you can think about funny ways of focusing light. Okay? So you can do that, you can control the properties of the output in situ. If you don't want to tune the system, you can use reactive mesogens to set the material. If you want to have a tunable system, but perhaps a little bit more rugged, then you use 3 or 4% of a reactive mesogen and make a very soft gel. You can do that. You can make the laser arrays, which will lead you to CW and RGB outputs. The LED work, though I didn't actually stress about that, was that's actually CW working, but not for very many seconds. Okay? But it does work CW. Right, I wanted just to, if I have 5 minutes, 4 minutes, 3 minutes, I just wanted to take you on to something. I could have given the same talk on displays, but with a different output. If any of you went to SID or ILCC a month or so ago, 2 months ago, you know that blue phases are a hot topic for display devices. And the reasons are you can control the colour in an analog fashion, that's how we do it. There's a threshold, you can multiplex the systems, there are no polarizers and field colour filters. So you can increase the pixel density, you can make 2-layer devices. And that's how we make them. The devices that were described in SID are not true blue phases, they are PDLC stabilized looking blue phases. So, before I stop, what's important, forget the top 2 from there, because that's the display aspect, which I will talk about on another occasion. But what's important here is we have very high efficiency single low lasers, 60%, 70%. If you make a reflecting device, you silver the inside of your device, you get 70% conversion efficiencies. You can do that in the chiromatic, you can make high temperature blue phase devices. And then just for fun, I brought along a little demonstrator. It's not a liquid crystal laser, but if you go to the Motorola website, you will find a telephone described called the Roca 8. Okay? And I didn't rightly say that you can make flexible displays, but this is a hybrid, light-emitting, LCD-controlled keypad that you can use in the dark. You can see it under the table, or if you take it out into bright sunlight, you can see it as well. In bright sunlight, you see the reflection from the emission fluorescence, like you do in a laser, from the layer that's underneath. And in front of that, we've got a controlling polymer film, a liquid crystal film, sorry. And that is, if you go onto the website, what is in the new Motorola displays, and that's a plastic device stuck onto the surface, keypad and display combined. I thought I might just tell you about that because I think it's fun. Okay, and I will stop there. Thank you very much for your attention.
We have some time for questions.
Anybody want to buy a phone? No? Yes, Robert.
So this may just very silly question, but you showed that using diode LED and generate laser. So what does that mean? It looks like the resolution of the wave spectrum is narrow because there is significance or
It was.
Would you repeat the question?
I think the question is, can you, tell me if I'm wrong, can you, with the AD pump laser, still get narrow lines? Yes?
Yes, I just want to know what the significance of that. Looks like just to me